machine learning for best linearized regression model using the HP prime. The talk has two milestones. It pushes the search for the best model in a new direction, a new milestone using machine learning, and it does it using the HP prime. It's a testament for the power and versatility of the HP prime, and kudos for Tim and Cyril and the rest of the team for creating this powerful machine. When I started the project, I said, I'm not so sure it will do it because the code is long and it does a lot of stuff, but came out like a champ. I want to dedicate this talk to a fellow in arms. I don't think nobody has met John Johnston in Australia. He was the curator for the HP Computer Museum. He has a lot of documentation on it. Fortunately, he passed away last April while climbing in Tibet. And the documentation he has is awful, and I really appreciate it. I guess he passed away doing what he loved, his other passion, climbing. First, we start with the history of best linearized regression models. The HP65 and HP67 stat packs offered regression programs for various models, but they didn't, you had to select the best manual. You had to try each one directly. It was the PPC ROM, if I'm not mistaken, that was the first ROM that had best fit selection, and then the Advantage, HP41C Advantage ROM also offered that feature. And all these programs focused on four, what I call standard models: the linear, exponential, logarithmic, and power. Of course, there are other popular transformation like 1 over x square root, which can be applied to both x and y. But of course, the more transformation you add, the number of models increases. Several PPC members explored obtaining best linearized regression models using a wider set. Bill Cole and his book over there is a testament of his Herculean effort to explore the various models. I wrote a lot of stuff about the same subject. Some of this was in the Corvallis library. Some of it is in previous HHC presentation. And also I did a lot of stuff for the HP solver, mainly as HP39G2 programs that also work with the HP prime. That's the good news. So it's not wasted effort. When you cover, now I'm talking about a large number, exploring many models in the tens or in the hundreds, depending on the number of independent variables. You have several choices how you manage the models. The first option is you set indices specifying all of the transformations for the model. So like number 1 is linear, number 2 is logarithmic, and that will specify the transformation for the variables. And you can do the same for multiple regression with 2 independent or 3 or more independent variables. Another approach, is to set enumerated transformations for each variable. And like 1 is linear, 0 is logarithmic, and so on. Here you add a little more complexity because now you use nested loops and you transform, you have combination of transformations, and then within the nested loops you do the calculations and then store the results aside and then sort or keep track or who is the best. And normally you should keep not just the very best, but maybe the top 10, 20, 50, whatever, depending on the total number of models you're searching. In the last few years, I began to focus on using a range of power applied to each variable rather than some enumerated transformations. And the two approaches, either we use integer values, ranges, like say from -4 to 4 in steps of 1. Or if you want to sort of have a higher resolution to study the curvature, you can do the same range but in floating point, in increments of half or 0.25 or even 0.1. That will give you even a higher resolution. Now all that is fine and dandy, but here's the problem. In my zeal to zoom in on the best regression models, I'm also catering to accommodate the errors. And these models will fit the actual data and the errors. And so if you come out with let's say you pick a model and you add intentionally some error, and you do this, the best model is not actually your theoretical model. Because of the error, some other models will be favored. So a machine language can help us in that department. To be more specific, this is part of supervised machine language. And supervised machine language uses two sets of data. The first set is used for training, for the calculations. And then the second set is used for testing. So we got these coefficients, how good are they? So each data should have a different noise. If possible, avoid taking one big data set and break it in half. It's better if you have two data sets from slightly different sources. So the basics for each model, we do the following. We calculate the regression slope and intercept, and then calculate the mean square sum of errors, MSSE1 for the training set. And then we calculate the similar statistics for the test set, but using the regression slope and intercept obtained by the training set, because we want to see how good the training set performed. And then we can calculate a weight MSSE value based on these two values. And the way I'm using it in the HP prime program is favors this factor. So if you use 1, you shift everything to MSSE2 and you focus only on the contribution of the test data. But I usually use a half, so I can still pay homage to both the training data and the test data. And then,
what is the training set?
We have two data sets. One we use to calculate the coefficients from the slope and intercept, and the other one we apply it on the other one, do projections and see how good are the projections matching the data itself.
So is it like every other data point? Was the
No, you have two separate sets.
Oh, unrelated.
Yeah. The better unrelated, the better. Some people just have a big set, they break it in half. Well, if you can avoid doing that, that's better. But and so then we calculate, we rank the models not based on correlation of determination, because really we're not calculating any of that for the test set, but we rank it on the MSSE value, the mean square sum of errors. Now we have some options in these operations. First of all, model selection. We can use enumerated the values for the transformation of x and y, as I mentioned before. Or as I mentioned before, we can use a range of powers that we apply to both x and y values in the case of linear regression. In the case with the power value of 0, we translate it to a logarithmic transformation. Also for handling data, we have options that I mentioned yesterday in tips and tricks. If your data is all positive and stays within the same kind of range, then you can use your x and y values without any transformation. You'll be fine. But if your data has negative values and varies widely, then you should normalize x and y, as I explained to you yesterday, using the minimum, maximum value, and then you map it on the range 1 and 2. That's the best I can recommend. You can also subtract the mean value and then divide by the standard deviation. And as I mentioned yesterday, well, you're going to end up in the minus 1, 1, and spread in either way, even if all of your data is positive. So I would say either do this or do this. Now, I'm also suggesting another method, the bootstrap method. Unlike the regular machine learning, we use a single data set. And in bootstrap thinking, or we repeat n times, selecting a different subset. And each subset has the same number of observations to calculate the regression statistics. And then we calculate the average slope, average intercept, and average correlation of the coefficient of determination for each model. And then we rank models by the average coefficient of determination. Now, to create and test data set, there's a file called popdata.txt. It's an HP prime file, and it has a function called popdata, and it has the following parameters: n number of points, x, the starting value of x, and then you have a, b, and I think this is an old file, Richard, I'm sorry. There should be an increment in x, and then a, b, and power are the coefficients that allow us to calculate y. And here I include two error coefficients, one that I use for the training data and one for the test data. Preferably they should be different. And the function will populate matrix M1 with the training data and matrix M2 with the test data. And here's a sample call for pop data. I want 101 points, starting at 1 in increments of 0.1, and A is 2, B is 3, and the power is 2. And then the maximum percentage of error for the training set is 10%, and the maximum error for the test data is 5%. Here's a sample output showing the leading and trailing elements of the training data in matrix M1. And here's a similar value, similar views, heading and trailing data for matrix M2, the test data. If you use normalization, there's a function called getMinMax, and it'll give you the minimum maximum value for your variables. I have two versions for the machine language. The first one is in this file, and it's called ML1, has 3 parameters. P data mat is the matrix that has the training data. P test data mat has the test data. And ML weight is the weight used to calculate stat. This weight tells us how much we lean on the training. So if I make it 0, that means that my results will lean entirely on how good the test data work with the calculated coefficients. The function returns a matrix with the columns of having R square, MSSE, numeric values for the Y transformation, X transformation, slope, and intercept. Here's a sample run. I call ML1 using the matrix M1, M2. The ML weight is half, and then I assign it to matrix M3. And the two views show the leading columns. This is R square. This is the MSSE, and it's sorted by these values. These are the same, the Y transformation, X transformation, and then you have the slope and then intercept column. ML2 is a similar function located in this file, and it has the same parameters. The only difference is it normalizes the values for X and Y, and gives you a matrix with very similar results. And again, here I'm using calling ML2 with similar arguments, storing the results in M5. And again, these are the results: the R square column, MSSE, the transformation for Y, for X, and then the regression results, the slope and the intercept. Bonus programs, after I've done this and was running fine, I went and I did a version that uses two independent variables. It'll do more calculation, it'll take more time, and I wrote similar programs. There's ML1 and ML2 in these files, and I also made the pop data 2, so you can populate M1, M2 with 3 columns of data, Y, X1, and X2. The Bootstrap regression, I use the function BSR in this file, and it has the following parameters. P data mat is the matrix containing the data. Fraction data used is the fraction of data used in each simulation, and of course the number of simulation. And then it uses normalized value of for X and Y, and it returns matrix containing R squared, Y transformation, X transformation, slope, and intercept values. And here's a sample run. I call BSR with M1. I'm using 60% of my data per simulation, and I'm doing 10 simulations. So it picks a random set of 60 elements, 60% of the data, and does the regression, gets the averages, and these are the average values, R squared. These are the transformation coefficients, and then the average slopes and average intercepts. Bootstrap uses a lot of that. Like if you do nonlinear regression and you want to calculate the confidence interval of your regression coefficients, then use Bootstrap to repeat it, because the process often involves random numbers, and then you just using the statistics you obtain, you obtain an average and then a confidence interval. And that's it.